Integration. Indefinite integrals. The inverse or opposite operation to differentiation is integration. Because the two processes are so closely linked, we would like the notation for integration to be consistent with that already introduced for differentiation. For example, if we differentiate x squared, we get 2x. We can write this as dx squared dx equals 2x. Integration should then reverse this process, i.e., if we integrate 2x, we should get x squared. To develop a notation for this consistent with differentiation, we proceed as follows. Dx squared dx equals 2x. Dx squared equals 2x dx. So basically we multiply both sides by dx. So we end up with 2x dx. We now introduce this symbol here called the integral sign. So it's like an elongated S called the integral sign to represent the inverse operation to the d in differentiation. Thus, the integral sign and d have the effect of cancelling each other, i.e. integral dx equals x. In the same way that sine inverse x equals x and the square root of x squared also equals x. So they cancel each other out. Then by equation 1, so equation 1 we worked out in the last slide to be dx squared equals 2x dx. So dx squared equals 2x dx. We apply the integral symbol to both sides, and the integral symbol and the d cancel, and we're left with x squared equals integral 2x dx, and then we just swap them around. Integral 2x dx equals x squared. So this is how we indicate that we reverse the operation of differentiation. We place the integral sign in front of the 2x and the differential dx behind it. Both are needed for the correct notation. The expression integral 2x dx is called the integral of 2x with respect to x and represents the function whose derivative is 2x. For this reason, it may also be referred to as an antiderivative. However, a problem arises. The integral, or antiderivative, of a function is not unique, unlike the derivative. Consider the following examples. So dx squared plus 7 dx equals 2x. So the derivative of x squared plus 7 is 2x. Therefore, the integral of 2x dx, or the integral of 2x with respect to x, is equal to x squared plus 7. In example 2, dx squared minus 3 dx also equals 2x, just as above. So the derivative of x squared minus 3 is also 2x. Therefore, the integral of 2x dx is x squared minus 3. So we had two different functions that gave us the same derivative. However, if we were to integrate the same derivative, we can come up with an infinite number of integrals. So what exactly does the expression integral 2x dx stand for? Once we note that dx squared plus c dx equals 2x, where c is any constant, we should realise that the integral, or antiderivative of 2x, will be all functions of the form x squared plus c, i.e. the integral of 2x with respect to x is equal to x squared plus c, where c is called the constant of integration. Because of the presence of the unknown constant of integration, this type of integral is called an indefinite integral, as distinct from another type of integral to be seen in the next section. So the other type of integral we will see is the definite integral. So the indefinite integral. If dfx dx equals f prime x, i.e. f prime x is the derivative of f of x, then the integral of f prime x with respect to x is equal to f of x plus c. This is the indefinite integral of f prime x, where c is the constant of integration. So what that basically means is, if you ever get the integral of a function, you must stick on a plus c unless you are told to do otherwise. In practice, to calculate integrals, we use a number of standard integrals and a few rules of integration. We now meet the first two standard integrals, which are given on page 26 of the formulae and tables. So standard integral number 1, the integral of x to the power of n dx, or with respect to x, is equal to x to the power of n plus 1 over n plus 1 plus c, where n is not equal to minus 1. And the second standard integral, the integral of x to the power of minus 1 with respect to x, is equal to the integral of 1 over x dx, which is equal to log base e, x plus c, which is equal to ln, which is the natural log of x plus c, where x is not equal to 0. So these are on page 26. Notice that in each case you add on a plus c, which is a constant. So here we have page 26, and here we have our first two integrals. Each standard integral can be verified or checked by differentiating the answer. Number 1, d dx 1 over n plus 1 times x to the power of n plus 1 plus c is equal to 1 over n plus 1 times n plus 1 times x to the power of n, which is equal to x to the power of n. So what happened here was we were differentiating with respect to x. So since the x is here, x to the power of n plus 1, we bring the power down in front, so the n plus 1 comes down in front, and we reduce the power by 1. N plus 1 minus 1 is n. And obviously to differentiate c, you just get 0. And then 1 over n plus 1 multiplied by n plus 1 is just 1. So you get 1x to the power of n, which is just x to the power of n. This is as long as n is not equal to minus 1, as then the denominator would be 0. Number 2, part 1. If x is greater than 0, then ln x, or the natural log of x, modulus, is equal to ln x, the natural log of x. Then d ln x plus c dx is equal to 1 over x. And part 2, if x is less than 0, then the natural log of x, of the modulus of x, is equal to the natural log of minus x. Then d ln minus x plus c dx equals 1 over minus x times minus 1, which gives us 1 over x. To use the first standard integral to differentiate powers of x, increase the index by 1 and divide by the new index. If the new index is a fraction, invert, so turn it upside down and multiply. Some examples are, so I'm going to go through these in more detail on the next slide, but if you're happy enough with where they come from, you can just skip forward. So to integrate, increase the power by 1 and divide by the new power. So the integral of x squared dx is going to be x to the power 2 plus 1 over 2 plus 1, which is x cubed over 3, which is a third x cubed plus c. You have to add on the plus c at the end. So the integral of x to the power 1 dx is going to be x to the power 1 plus 1 over 1 plus 1, which is x squared over 2, which is a half x squared plus c. So the integral of 1 dx, well, that's the same thing as getting the integral of x to the power 0 dx, and that's equal to x to the power 0 plus 1 over 0 plus 1, which is x to the power 1 over 1, which is x plus c. So the integral of 1 is always x plus c. And the integral of 1 over x to the power 4 dx is the same thing as getting the integral of x to the power minus 4 dx, which is equal to x to the power minus 4 plus 1 over minus 4 plus 1, which is x to the power minus 3 over minus 3, which is minus a third x to the power minus 3 plus c. So each time what we did was we increased the power by 1, so we added on 1 to each of the powers, and then we divided by the new power. If the new power is a fraction, invert, which means turn upside down, and multiply. So the integral of root x dx is the same thing as getting the integral of x to the power of a half dx. So again, we add on 1 to the power, and then we divide by the new power. So we get x to the power of a half plus 1 over half plus 1, which is x to the power of 3 over 2 over 3 over 2. So this line means divide. So we change divide to multiply, and we turn the second fraction upside down. So x to the power of 3 over 2 times 2 over 3 is 2 over 3 x to the power of 3 over 2 plus c. Example, part 1. Write down 3 antiderivatives of x to the power of 4. So 3 antiderivatives are a fifth x to the power of 5, a fifth x to the power of 5 plus 8, a fifth x to the power of 5 minus 12, and so on. You can add on any constant you want. In this case, the constant is plus 0. So the rough work to get that, the integral of x to the power of 4 dx is equal to x to the power of 4 plus 1 over 4 plus 1, which is x to the power of 5 over 5, which is a fifth x to the power of 5. So find the integral of x to the power of 4 dx. Well, the integral of x to the power of 4 dx is a fifth x to the power of 5 plus c. Two rules of integration are given below. Rules of integration. Let u and v be functions of x and c be a constant. 1. The integral of c times u dx is equal to c times the integral of u dx. So basically you bring the constant out in front of the integral. And 2. The integral of u plus or minus v dx is equal to the integral of u dx plus or minus the integral of v dx. So you just break them apart and you do the two integrals separately. These two rules can be derived from similar rules for differentiation. The first rule says that a constant multiplied by a function of x can be removed outside the integral. This is really important and will help us down the line with harder questions. The second rule says that the sum or difference can be integrated separately. So we break them apart and integrate them separately. In each case, we only use one constant of integration. So just add on 1 plus c. Example, find the integral of 4x squared dx, the integral of x cubed minus 5 over x plus 3 dx, and the integral of x plus 1 squared times x minus 1 dx. So let's start off with the integral of 4x squared dx. So we're going to take the constant outside. We're going to stick it in front of the integral. So now we're integrating x squared dx. So x squared, we add on 1 to the power, so we have x to the power of 2 plus 1, and we divide by 2 plus 1, and we have the 4 in front, and we add on a plus c. X to the power of 2 plus 1 is x cubed, and 2 plus 1 is 3, so we end up with a third x cubed with the 4 stuck on in front plus c. And 4 times a third is 4 over 3 x cubed plus c. So we multiply in the constant at the end. Next, find the integral of x cubed minus 5 over x plus 3 dx. So the integral of x cubed minus 5 over x plus 3 dx, we separate the functions. So we have the integral of x cubed dx minus 5 times the integral of dx over x plus 3 times the integral of 1 dx. So again, we brought the constants outside, so the minus 5 came in front of the integral, and the 3 came in front of the integral, because minus 5 multiplied by dx over x is actually minus 5x dx, and 3 times 1 dx is really 3 dx. So we've taken the constant out in front of the integrals. And just to note, dx over x is the same thing as 1 over x dx. So it's just writing it a different way. Okay, so now we integrate. So x cubed dx, so we add on 1 to the power, x to the power 3 plus 1 over 3 plus 1, gives us x to the power of 4 over 4, which is a quarter x to the power of 4. So again, the minus 5 is brought out in front, and to integrate dx over x, which is really 1 over x dx. So the integral of 1 over x is the natural log of x. So we get ln x, the natural log of x. And then the integral of 1, well, 1 is really x to the power of 0. So x to the power 0 plus 1 over 0 plus 1 gives us x to the power 1 over 1, which is x. And 3 times x is 3x. So we have a quarter x to the power 4 minus 5 natural log x plus 3x plus c. Don't forget about your plus c at the end. Part 3. The integral of x plus 1 squared times x minus 1 dx. So we multiply out the brackets first. So the integral of x plus 1 squared times x minus 1 dx is equal to the integral of x squared plus 2x plus 1 multiplied by x minus 1. So multiplying out this gives us this. And then multiplying out again, we get the integral of x cubed minus x squared plus 2x squared minus 2x plus x minus 1 dx. And then simplifying, we get the integral of x cubed plus x squared, so these go together to give us x squared, minus x, so these go together to give us minus x, minus 1 dx. Now we integrate separately. So x cubed, we'll have x to the power 3 plus 1 over 3 plus 1, which is a quarter x to the power 4. X squared, we have x to the power 2 plus 1 over 2 plus 1, which is a third x to the power 3. Minus x, we have minus x to the power 1 plus 1 over 1 plus 1, which is a half x, minus a half x squared. And minus 1, we have minus x to the power 0 plus 1 over 0 plus 1, which is minus x. And don't forget to add on your plus c. So reminder, here's page 26 of our formula book, integrals. And so far we've just used the first two formulas. But in later videos we will be using the rest.